Okay, so that's fluorescence. One thing I did want to add about this idea of, let me get a energy level diagram for, yes mate. For hydrogen, actually we'll take this picture here. I hope you're all familiar with this picture now. The Lyman series, the Balmer series, and the Passion series, these energy jumps are quite large. They result in UV ray photons. We did a calculation earlier. The Balmer series result in visible photons, or most of them do. There's one UV photon there, or infrared photon, I can't remember which. And the Passion series results in infrared photons. You'll notice the energy jumps visually appear to gradually get smaller and smaller. Now, I hope you know this diagram because I'm going to make it quite small now. There's something that I need to qualify, something that I didn't probably make, or well, I don't feel like I made clear enough. Now this is an atom, isn't it? You could imagine this is a hydrogen atom. Never happens in our experience, a hydrogen atom by itself, but it's a simplistic view of what we're trying to explain. Hydrogen atom. And this is energy levels in the atom. Those energy levels are very specific. The energy jumps are very specific, very discrete is what we say. If I shine light on this substance and white light, say, so white light has some green in it, has some yellow in it. I'm not putting these in order. Has some orange, has all the colours of the rainbow. So you could imagine this is sunlight maybe. Some red, blue and purple. You get the idea. We see that as just very plain white light. If I shine that light on that, or I had a bunch of these atoms in a small box, and I looked this way using a spectroscope. So this is me looking with a spectroscope. And this atom, or the atoms that make up that gas were in their ground state. What would we see through the spectroscope? Yeah, we would see the entire visual spectrum, wouldn't we? So now let's just hydrogen spectrum. I'll just get a hydrogen spectrum here. This one will do. Now, I may have misled some of you in that, is this what I see? Now there's a, uh-oh. Oh no. I'll try again. All right. Now, is this what I see? Now we don't see the emission spectrum, do we? Because that would have to be the excited atom. Would I be seeing this through the spectroscope? What would be happening is, okay, I shine white light through this gas, which is hydrogen. I look at it through the spectroscope. In the spectroscope, I see the continuous spectrum. I don't see these dark lines when the hydrogen is in its ground state. Why? Well, it's not necessarily going to absorb those colours. Yeah, that's right. So visible light, look at this. This is just visible light. I say just. It is visible light, visible region of the spectrum. In the visible region, now remember that this atom is in its ground state. It needs to make a minimum discrete jump up to here to the first excited state. But if I'm just shining white light on it, I can't make that jump because white light is these jumps here. They're not big enough to make the jump. This atom has to be, or these atoms have to be excited. They have to be heated. They have to be heated quite a lot, actually. Hang on, what's going on here? I can't select it. Here we go. Put this up here. I don't see this unless I add heat. So let's add some heat, quite a lot of heat to this atom. That's me drawing a flame. Okay, heat. Looks like a raindrop. Draw some red in there. Okay, and I'll call it heat. I need to heat it quite a lot. And you can see that if I add heat to this atom, sufficient heat, and what is heat? It can't just be infrared radiation, can it? Because once again, we don't get excited enough. It has to be radiation that is sufficient, which includes some of the UV spectrum, such that we can make these jumps up to this excited state at the minimum, so that we can emit these lines, or so that we can absorb these lines here. Okay? So then so this is super hot. This atom is super hot. We shine white light through it. We look at it through a spectroscope, and we see that these lines here, these dark lines, are scattered. Okay, so then what happens is, because of these absorptions, we have scattering of these colors, and the dark lines appear. Okay. Is that clear? I better write something about that, I suppose. What did I write? The gas, in order to scatter some of the Balmer series. So it needs to be in an excited state in the first place. And we might say the gas needs to be very hot. It doesn't look like hot, does it? Very hot. You can't just, what I'm saying is you can't just take a cylinder full of hydrogen, look at sunlight through a spectroscope and expect to see these lines missing. That's just not going to happen. Okay, that's the end of structure of the atom.